All right, AP Chemistry. This is the day 96 lesson on weak acids and the common ion effect. All right, so you receive that on Tuesday, and we're going to try to get that done by Thursday. So the pre-assignment is all on the lecture video, so you should watch the lecture video. I'll just state what these are quickly. It's the concentration of hydroxide ions. That's what defines a base solution, and it's the concentration in the solution. The more hydroxide, the more basic the solution is. H plus or H3O plus is the concentration of hydronium ions in the solution. The more of these, the more acidic the solution. pH is simply a user-friendly scale to measure how acidic or basic a solution is. The lower the pH, the more acidic the solution is. So 0 is extremely acidic. 14 has virtually no acid in it. And pOH is a measure of the hydroxide ions. It's a scale. It's the reverse of the pH scale. All right, so we're going to be able to figure out all four of these. All right, and the common ion effect, what does it have on the final pH? So in an acid reaction, if you put one of the product ions in the solution, the reaction will not be able to run in the forward direction as well. And therefore, less of the hydronium ions are going to be able to be produced, and the solution will be less acidic. The best way to understand it is to see the example that you'll see in this answers video. All right, so let's get going. So what is a Ka value? It's the acid dissociation constant. Okay, so it's the acid dissociation constant that measures how strong an acid is. It's going to tell you how far from left to right, from reactants to products, that an acid reaction will go. And the farther to the right it goes, the more hydronium ions it produces, the more products, hydronium ions, H3O+, and that means it's a stronger acid. So the bigger this number is, the stronger the acid. Okay, what are the conjugate bases of the following acids? So conjugate base. Okay, so conjugate base differs from its conjugate acid by 1 proton. So these are all acids. So the conjugate base would be this. So that hydrogen was released, only the proton, not the electron. So it left the electron behind. That's why this becomes a negatively charged conjugate base. So conjugate acid, conjugate base, and they differ by that 1 proton. This one. Again, this is a proton that came off, there it is, and it leaves behind this molecule, the rest of it, and the electron it left behind as well, so it's a minus charge there. And Hi, same thing, it's going to be simply, this one's simply going to be I minus and H plus. Okay, that's the conjugate base, conjugate base, conjugate base. Okay, what are the conjugate acids? So these are bases. That means they're going to accept a proton. So if NH3 accepts a proton, it becomes NH4 plus. That's the conjugate acid of ammonia. That's ammonium. Okay, this one, you're just going to add a proton on there. So it becomes this. Like that, it just added a proton on, so the difference between these two is 1 proton. And this one, okay, and we're going to go ahead and add the proton there, so there's the hydrogen 5, now it's hydrogen 6, and it has a plus sign because it was just a proton, it didn't bring the electron along. Okay, write the long form reaction for the following acids in water. So long form is this. I'll just go ahead and continue it from here. You add H2O. Okay, it's a weak acid, so it's a reversible reaction. You know it's weak because it's not one of the 7 strong acids which you need to memorize. So when this proton jumps over onto the water, it becomes a hydronium ion, and then you have the rest of this as a conjugate base. Okay, and then finally, hydrofluoric acid. It looks like some of the strong acids, like hydrochloric or hydrobromic or hydroiodic. Those are all strong. This is a weak acid, however. We'll talk about that at a later time. Okay, that's the long form of each of those. Write the long form of a generic reaction. So you want to learn to write generics, because if you get some acid by name that you don't know the formula for, you use the generic formula. Okay, so it would be this. You broke that off, it joined the water to become that, and then the rest of it was left behind with the electron, so it's that. Okay, write the short form generic reaction for a weak acid, so it's simply this. You omit the water on both sides. And there it is, okay? All right. All right, weak acid reaction of hydrofluoric. HF is a weak acid. It gives you the Ka at 25 degrees. And we always assume in acid problems we're at just room temperature, 25 degrees centigrade. The Ka is a constant number, okay? How much that acid is going to dissociate in water is going to be fixed at a certain temperature, 25 degrees. Okay, so let's go. This is just a rice table problem. So here you start off with HF. And acid problems tend to be kind of easy in the sense that their coefficients are always 1, and it's going to produce, whoops, I should actually write the long form. I told you that's what they prefer on the AP. You don't have to write the plus signs. Okay, so there's the reaction. The initial, it gives you an initial of 3. I'm not worried about decimal points here. You don't ever include water because it's a pure liquid. And you assume that you start off with nothing here and nothing here. Now you're going to subtract 1x because the coefficients are all going to be 1s, so you don't have to put any numbers in front. And so this is going to be 3 minus x. Now this is on the product side. You're going to be adding the 1 coefficient and x, so it's 1x because the coefficient there is 1, and that gives you x. And now this same thing, the coefficient in front of f is 1, so it's plus x, so it's x. All right, so you have your algebraic expression. Now we write the law of mass action for this reaction. We don't include water. So it looks like this. The acid dissociation constant equals the products on the top over the reactants on the left side. Without water, it's just HF. Now we can plug in, we'll come over here and we can plug in our expressions there. And we'll go ahead and put the number in now. So it's 7.2 times 10 to the minus 4. Equals x, the products on top, x, those two right there, x times x, over 3 minus x. Okay, and the simplifying assumption says that if x is very small compared to our initial concentration, and we're going to assume it always is, that you can get rid of it, okay? So I'm going to come down here and just do the math. Okay, there we go. We're going to multiply both sides by 3. And what we get is x squared now you need to take the square root of both sides to get x. Okay, so let's be sure you do that. You need the square root of 21.6 times 10 to the 4th. So I'm going to come up here, try to get the glare off, and I'm going to hit second x squared down here. That gives me the square root symbol, and it's 21.6 times 10. This thing's called a caret, negative 4, and close the parenthesis and hit equal. And that equals 0.046. And that's a molarity, so it's molar. So what does that mean? One thing we always want to know is the hydronium ion concentration, so that's x. X equals that, and that's what X is. So that's going to be 0.046. Also this one, 0.046. That's what X equals. We might not care about that concentration, but we might as well write it in. And this one is 3 minus 0.046, and that's going to equal 2.95. So this equals 2.95. So you can see not very much of this dissociated. It went from 3 molar down to only 2.95. That's not a very big reduction. And the amount produced over here was a very small amount of the hydronium and the fluorine. That's pretty typical for a weak acid reaction, okay? So let's answer these questions. What is the hydronium ion concentration? It's that right there. Don't assume it's always X, but it pretty much always is. It's not this, it's what this is up here. So that's this, hydronium, 0.046 molar. What is the pH? So go to your acid-base roadmap. So now we plug in the number. Okay, and so we have the negative. Use this negative sign down here. Log, regular log, not natural log. 0.046. Close the parenthesis, and you get 1.3. Okay, that's still not a strong acid, even though it's approaching 0. Hydrofluoric acid is a strong weak acid. It's a fairly strong weak acid. So again, the pH there is 1.34, I'm going to call it. That's the pH. All right. What is the hydroxide ion concentration? Okay, so there's a formula on your acid-base roadmap, and it looks like this. Hydroxide times hydronium equals 10 to the negative 14th power at 25 degrees centigrade, okay? So I'm going to come over here and plug in those numbers. I'm actually going to solve for OH. So we're going to divide both sides by H3O. So let's do that. So it's 10. Okay, so this is going to equal 10 to the minus 14th over this number, the hydronium ion concentration. And that is going to gives us this very small concentration. If it's primarily an acidic solution, it's going to have a very small concentration of hydroxides. So that's 10 to the minus 13th, and that's molar. Okay, so 2.17 times 10 to the minus 13th molar. All right, that's the hydroxide ion. Okay, now we want to know the POH. So POH, get this off your acid-base roadmap. All right, so let's do that one together. So it's negative, this time down here, negative log, okay, and it opens a parenthesis there, and it's 2.17 times 10 caret negative 13. Close the parenthesis and hit that, and it gives you 12.7. And something you'll notice is that the pH, which is just roughly 1.3 plus 12.7 equals 14. So pH plus POH is going to equal 14. So the other way I could have gotten that is 14 minus 1.34 would have given us 12.66 or 12.7. We could have done it. That would have actually been maybe a simpler way. Okay, now we're going to justify that eliminating the X right here, that we eliminated that, is justified. So we're going to use the 5% rule. So what you do is you take your value of X, which is 0.046, as a percentage of the initial concentration of the acid of 3. So we come down here, and you multiply it by 100%. Just by 100, and then you put the percent sign on at the end, and what that would give us is 1.5%. So that is less than 5%. So we justified eliminating the X right there. Okay, that takes care of this problem. Okay, now we're going to do one with a common ion. All right, so we have the same situation, same Ka, same HF, but now the solution contains a common ion Kf. Now, if you look at your solubility rules, potassium will dissolve 100% with anything, totally. So that means this reaction of this could be written as this, Kf. It's reversible. Well, really, it's not so much. It won't come back together. It doesn't matter. So that's going to produce a K ion, K plus an F minus ion. Okay? Now, if you look at this reaction that we just dealt with, or not the one we just dealt with, this hydrofluoric acid, the acid that we're going to put in the rice table, it's also going to produce an F minus. So let's go ahead and write the equation here for HF. So in other words, this also produces an F minus ion. This produces an F minus ion. So what you're going to do is you're going to say, you're going to put this in first. It doesn't matter what order, but we'll just say you put this in first. So that means you're going to have some of the F minus ion in solution. It's not going to be 0 at the beginning like it was on the previous problem where you didn't have any of this conjugate base here. All right, so let's plug in the numbers. And well, first of all, we need to know what is the molarity of that. So if you started off with 1.1 molar of Kf, you'll end up with 1.1 molar of K and 1.1 molar of F. It's going to break up. It's going to produce as many Ks as Fs as it originally had. Okay, so let's go ahead. The concentration of HF is 3. We don't use water because it's pure liquid. Then H3O, we start off with 0. We assume we have none. And then we're going to assume that the common ion, we started off, we know we put this molarity in, 1.1, it totally broke up into 1.1 K and 1.1 F minus. We don't care about the K in this problem. It's spectator. It just goes off to the side. So this is what's going to be our initial concentration in this common ion problem. Okay, again, this has the same ion F minus as HF does, F minus. All right, so again, these rice tables become really easy. After a while, they all have coefficients of 1. So this is going to be 1.1 plus X. Okay, write the law of mass action. So it's these two and this only, not the water. Okay, now we're going to go ahead and plug in the algebraic expressions. Again, what you're putting in always in a law of mass action equilibrium equation is the equilibrium values, nothing up above, only these. Okay, so it's going to be this. Now in the last problem, it was just another x, but now it's 1.1 plus x, and it's over 3 minus x. Okay, so now we're going to, I'll do two things on the next step. I'll substitute in the actual Ka number, 7.2 times 10 to the negative fourth, and I'll do the simplifying assumption. So it's x times, now we're going to eliminate both of these x's, the one on the top and the one on the bottom. Any addition, subtraction, you can eliminate the x if it's very small. So it's x times 1.1 over 3. Okay, so I'm going to come over here, and it's going to be x equals, I'm going to multiply both sides by 3. Cancel, cancel, and divide both sides by 1.1. Cancel, cancel, so all I have left is the x. So x equals 3 times 7.2 divided by 1.1. And don't forget the 10 to the minus 4. So I'm just do 3 times 7.2 divided by 1.1. That gives us 19.6 times 10 to the minus 4. Okay, so that means this number is the X right there. It's the hydronium ion concentration. There it is. I'm not going to worry about adjusting the decimal right here. You could do it. and this is 1.1 minus this number. So this is a very small number. It's really 0.00196. So 1.1 minus 0.00116 is going to be a very, very small number there. Okay, so this is your H3O. So what will happen to the HF as soon as it enters the solution? It's going to dissolve. It's going to break into K plus and F minus ions. Okay. All right, and what is the hydronium ion concentration? Well, X, it's whatever X is, and X is this. So it's this. There it is. What is the pH? It's the negative log of the hydronium ion concentration. So I already wrote the formula earlier, so I'm going to say negative log of 19.6, 10 to the negative fourth. Okay, so we'll do that. I won't do it on screen. Negative log 19.6 times 10 caret negative 4, close the parenthesis, and I get 2.7. So that's still a weak acid. It's getting in the low end of the 0 to 14 range, but you really have to be 0 or 1 to be a strong acid, okay? Hydrofluoric acid is a weak acid. All right, what is the hydroxide ion concentration? Well, I tell you what, I am going to figure out, I'm going to figure out this. I'll just to show you can do it in a different order. What is the POH? So the pH, whoops, down here, sorry. pH plus POH, again, get this off your acid-base roadmap, equals 14. Okay, so the pH we just said is 2.7 plus POH equals 14. So you're going to subtract 14 minus 2.7. That's going to give you 11.3. So POH equals 11.3. Okay. And finally, what's the hydroxide ion concentration? So hydroxide ion, I find this to be an easier calculation than going the other way. OH minus equals 10 to the negative POH. Again, acid-base roadmap gives you all these formulas. You'll eventually have them memorized just by doing enough of these problems. And so it's going to equal 10 to the negative 11.3, which equals, it equals 5.0 times 10. And don't forget, I'll show you this, don't forget that exponent there, okay? You forget that, it's all wrong. Okay, to the negative 12, very small, and that's a molarity. So compared to the acid concentration, hydronium, 10 to minus 4, this is a really tiny number. Okay, and now it doesn't ask you to do the 5% rule. It says compare the pH of the previous two reactions and explain why the second reaction is a lower H3O plus concentration and higher pH. So for this one, the pH, so this reaction, common ion, was 2.7 pH. Okay, no common ion, that was the last reaction. Hang on a sec. Yeah. Last reaction was 1.34. So that means, well, let's just write that. So pH for no common ion equals 1.34. So this is more acidic. And this one is less acidic. And why is that? Be sure you can explain it. Because if there's no common ion, that's a 0 at the beginning, then it's easier for this reaction to flow to the right. The moment, according to Le Chatelier's principle, that you put some of this in the solution before you even start the reaction, then this side of the equation becomes more crowded, the room becomes more crowded, and it's harder. It doesn't necessarily flow backwards, but it's harder for the reaction to flow to the right because the room over here is more crowded. Therefore, you're going to produce less hydronium ions, so it's going to be a less acidic solution with a higher pH. Higher pH means less acidic. Okay, and so that's what you have here. You have you have no common ion. That's the last problem. Is this? This problem was 2.7 right there. So it's a less acidic solution with a common ion. Okay, I'm going to go ahead. Next problem is 7. I'm going to go ahead and end this video, and I'm going to put 7 and 8, which we did in class. I'm going to put them on a separate video. Okay, so you can pick those up later.